All right, today we're jumping into a concept that is absolutely fundamental to building any big, scalable system: consistent hashing. I mean, this is the secret sauce that lets huge services grow and even shrink without everything just falling apart. So let's get right into it. Okay, just picture this for a second. It's a total nightmare scenario, right? Your service is exploding, users are pouring in, so you do the logical thing. You add another server to handle all that new traffic. But what if adding that one server meant you had to move practically all your data? Every user profile, every picture, every piece of information just shuffled around to a new location? That's the kind of catastrophe consistent hashing was invented to stop.
Yeah, so let's put a name to this headache. We're going to call it the data shuffle problem. And it's exactly what happens when you use a really simple, but maybe too simple way of spreading your data out. So on the left, you've got the old school way, standard modulo hashing. Let's say you have, I don't know, 10 servers. You could just take a piece of data's unique ID, its key, and divide it by 10. The remainder, that's the server it goes to. Super simple, seems fine, right? Well, here's the catch. The moment you add an 11th server to handle more load, your formula changes. Now you're dividing by 11. And suddenly, the remainder is different for almost every single key. It's complete chaos. You're remapping everything. Now look at the right. That's the promise of consistent hashing. You add a new server, and only a tiny, predictable slice of data has to move. It's stable, it's calm, it's how you actually scale.
So, how in the world do we get from that chaos to this calm, stable system? Well, the solution is it's actually really elegant. It's all about getting rid of that straight line of numbers and starting to think in a circle. So here's the core concept. With consistent hashing, what we do is we take everything, our servers, our data keys, all of it, and we use a hash function to place them on the edge of the same imaginary circle. And the whole point, the absolute key takeaway, is that by setting things up this way, we make sure that whenever we add or remove a server, the amount of data we have to move is tiny, just minimal destruction. Okay, so let's walk through exactly how you'd find where a piece of data lives. It's just a few simple steps. First, you place your servers on this circle. You just hash their names or IP addresses to get their positions. Step 2, you take your data key, whatever it is, and you hash it too, so it lands somewhere on that same circle. Then, step 3 is easy. From your data's point, you just start walking clockwise around the ring. And finally, step 4, the very first server you run into, boom, that's the one that stores your data. It's really that straightforward. Hash your key, walk clockwise, and find the next server. And this is where the magic really happens. Look what happens when we add a brand new server. Let's call it server E. It lands right here between server A and server B. Notice something? Server C and D don't even know it exists. They are completely unaffected. All that happens is server E takes over the keys that live between it and server A, keys that just a moment ago belonged to server B. The impact is totally localized, and it works the other way too. If server A suddenly goes offline, its data doesn't just get lost. It's automatically picked up by its clockwise neighbor, B. The ripple effect is contained. It's not a system-wide tidal wave. And here's the beautiful math behind it. This is the payoff. When you have n servers and you add just one more, the amount of data you have to reshuffle is, on average, just 1 over n plus 1. Think about that. If you have 100 servers running and you spin up number 101, you only have to move about 1% of your keys. That's it. Compared to the old way of moving almost everything, this is an unbelievable win for scalability. Okay, so that sounds perfect, right? Problem solved? But of course, there's a little bit more to the story. This simple circle has a potential weakness. What if the hash function doesn't space our servers out nicely and evenly? That brings us to the next really clever trick, something called virtual nodes. And yeah, this is a very real problem because hash functions are kind of random. You could easily end up with a situation where 2 of your servers are clumped really close together on the ring, and then there's this huge empty gap before you get to the third one. What does that mean? It means that third server gets stuck with a massive chunk of the work, a huge arc of the circle, while the other 2 are barely doing anything. You get these massive load imbalances. We call them hotspots. So what's the fix? Well, it's brilliant. Instead of putting each physical server on the ring just one time, we pretend it's many different servers. We give it lots of virtual spots. So server A isn't just one point anymore, it's A1, A2, A3, a whole bunch of points scattered randomly all over the ring. By doing this, we basically smash those big uneven gaps into tons of tiny little pieces. The result? A much more balanced distribution of data. And again, the math backs this up. The more virtual nodes you add, the more you shrink the variance, which is just a fancy way of saying the difference in load between your busiest and least busy server. Typically you'd use something like 100 or 200 virtual nodes for each physical machine. The more you use, the more evenly everything gets spread out, and the more predictable and stable your whole system becomes. Okay, so let's talk about what this means for actual performance. Because for any engineer, this is where the rubber meets the road, right? We need to know how fast this thing actually is. The biggest win here is the lookup speed. Finding which server a key belongs to is crazy fast. We're talking O log m, where m is the total number of virtual nodes. Now, log m just means we don't have to scan through every single node on the circle. Instead, we can use a really smart search, like a binary search. It's kind of like looking for a word in a dictionary. You don't start at A and read every page. You open it to the middle, see if you need to go forward or backward, and repeat. It's super efficient. And the amount of memory you need just grows linearly with the number of nodes, which is totally fine. So if you were going to build this, how would you actually store the ring in memory? Well, you've got options. You could use a simple sorted list of all the node positions. That's easy, and it gives you that super fast binary search for lookups. The downside? Adding or removing a server means you have to rebuild parts of the list, which can be slow. For a system where servers come and go all the time, you'd probably use something more advanced, like a balanced binary tree. That gives you fast lookups and fast updates. It's a classic engineering trade-off, simplicity versus performance. And I just want to be clear, this isn't some abstract academic idea. Consistent hashing is the invisible engine behind some of the biggest services you probably use every single day. I mean, it is literally everywhere. Big distributed caches, like Memcached, they use it to split up data across machines. The famous Amazon Dynamo paper that basically laid the blueprint for a lot of NoSQL databases, that was all about consistent hashing. Even the load balancers and content delivery networks that send you videos and web pages, they use it to figure out which server to send your request to, and to do it reliably. Now, to be fair, it's not the only way to solve this problem. There are other cool techniques out there, like rendezvous hashing or Google's jump consistent hash. They all have their own unique pros and cons. But this simple, elegant, circular model of consistent hashing has really stood the test of time. It just hits this sweet spot of performance and flexibility that makes it super popular. Okay, so let's wrap this all up. If you're going to remember anything from this, let it be these 4 things. Number 1, you map everything, keys and servers, onto a circle. Number 2, to find where data lives, you just walk clockwise. Number 3, you use virtual nodes to keep the work spread out evenly. And number 4, the big payoff. When things change, when you scale up or down, the data movement is absolutely minimal. And that kind of brings us to a final question. Consistent hashing was this massive breakthrough. It solved the huge scaling problem of the 2000s, this whole data rebalancing nightmare. It's what gives modern systems their elasticity. But systems never stop evolving, right? New problems always pop up. So the question is, what's the next big bottleneck? What's the problem that even a clever solution like consistent hashing can't solve by itself? Something to chew on.